Let's look at some information that you should know prior to entering this class. Hopefully this will be a review for you. First off, I just want to take a moment to address that there are two different types of observations. We can have both quantitative or qualitative values. Qualitative is going to be descriptive things. Quantitative, we're going to be working specifically with numbers. So in this class, the majority of what we do is going to deal with quantitative values. So we're going to have lots of numbers. We're going to be talking about variables that are usually things that we can measure. Some we're going to calculate, some we will measure with tools in the classroom, but quantitative values is primarily what our focus will be. For the examples that we see here, the right-hand side is quantitative, and if you'll notice, we have numbers here, and then they're all followed by something. So 10 inches, 14 inches, 8.5 pounds, 140 square inches, $300. These are not only numbers, but these are numbers that are accompanied by some sort of unit. And so those units are going to give meaning to those values. 10 is just a number. $10, 10 cents, 10 hours. By putting that last little bit of information, that unit after the 10, now that number 10 has meaning. Now we understand what that value should represent. So in this class, since we are dealing with lots of different measurements, these measurements are going to have units that accompany them. You will be responsible for understanding what units your values need to be in for you to perform your calculations. And if it's not in the proper unit, you will be responsible for converting that into the appropriate unit. The scientific method is a process that you, I'm sure, learned several years ago. I just wanted to review them with you. Whether we are doing a virtual lab or we're doing an in-person lab, think back to the science fair projects that you did when you were younger. They all follow the same general process or procedure, and this is called the scientific method. We start off with a purpose or a question. If you have no knowledge about that situation or topic, then you will probably need to go do some research. In our class, you're going to have lessons. You may have something to read specifically that goes with the lab, but there will be some sort of research aspect to the process. You'll have a hypothesis. So here is where you make your prediction. If you are conducting an experiment like you would in a science fair project, you probably didn't know the expected outcome, so you genuinely were just making your best guess. Here in class with what we're studying, based off of the lessons, you should have some idea, some expectation as to what the outcome will be if this is a topic that we have already learned prior to doing the lab. So you should be able to formulate some sort of hypothesis there. You will perform the experiment, you will analyze the data that you collect, and then you will form your conclusion. Please make sure that you know what the steps of the scientific method are in order, because you will be tested over that knowledge. Let's talk about conversions now. When we are converting, we are taking a value and we are simply saying, what is that equivalent to if I were to measure it with a different unit, with a different tool? So if we are talking about distance, if I'm measuring how far away I'm standing from the door, and let's say that I have a regular ruler, well, I could measure my distance in inches, or I could measure my distance in feet. Now, if I say that I am 2 inches from the door, or I say that I am 2 feet from the door, since those are two different units of measurement, they have two different interpretations. If I tell you that I am 2 feet from the door and I say, I wonder how far away that would be in inches. Well, I would not change what my location or my distance is from the door, but instead of saying 2 feet, I would then calculate that that would be equivalent to 24 inches. I'm still the same distance away. 2 feet, 24 inches are the same measurement, but because I used a different unit, then they're going to be represented with different numerical values. So that's all we're asking you to do with our conversions. Dimensional analysis is a process where you take the unit for a value that you were given and you multiply your number by some ratio, by a fraction, that takes the unit that you are given and it changes it into the unit that you need your measurement to be in. Now, ideally, we can just go from one unit to the next. Sometimes we have to put a little chain of conversions together in order to make this happen. But this is what we're doing when we are talking about dimensional analysis. So for example, if I say that I am, let's just stick with my example of 2 feet from the door. If I wanted to know how far away this is in inches, then I would need to set up a fraction that tells me the relationship between feet and inches so that I know what to multiply or divide by. I need you to understand that this is the same thing as 2 over 1. And then, remember, all whole numbers go in the numerator, so 2 over 1 is just simply taking that whole number and writing it as a fraction, but this is exactly the same value, all right? Now, I'm going to multiply that by a fraction. Now, how do I know what needs to go in the fraction? Well, let's pause from our dimensional analysis for a moment, and let's just talk a little bit about math in general. We should understand that 5 divided by 5 gives me a value of 1. If I were to do 100 divided by 100, I still get a value of 1. If I take my unit and I attach it to the number, so let's say that I have 5 seconds divided by 5 seconds. Well, my 5s are going to cancel out. They simplify to a value of 1. But my units are going to be treated just like numbers. So just how 5 divided by 5 is 1, or for that matter, anything divided by itself is 1, that's true for my units. Seconds divided by seconds is going to simplify to a value of 1. And since we are multiplying fractions in dimensional analysis, if I multiply anything by 1, that number doesn't change. So in other words, 5 times 1 is 5. 10 times 1 is 10, right? So we are going to take this concept of dividing by itself and we're going to apply it to our dimensional analysis. So we have 2 feet, where feet is currently in the numerator. That means that I need to put feet in the denominator. This is going to allow me to have feet in both the numerator and the denominator once I multiply across, thus making it cancel out. I'm going to go from feet to inches. So inches goes in the empty spot, which in this case is the numerator. Now I need to put my values in. A ratio is just simply telling me how two things compare to each other. So the easiest way to approach this is to start off by deciding which value or which unit should receive a value of 1. So I say that the larger one gets the 1. Whichever unit of measurement is larger gets the number 1 written in its place. So a foot is larger than an inch. So I'm going to put a 1 in the denominator with foot, because that is the larger unit of measurement. Now I'm going to ask myself, how many inches does it take to make a foot? It takes 12 inches to make a foot. So by putting the values in to show how these two units relate to each other, I have now written my fraction. we are multiplying across. So 2 times 12 is 24 feet times inches. And then I have 1 times 1 is 1 feet. So let's go ahead and address the obvious. Numerically speaking, 24 over 1 is just 24. If I look at my units, I see feet divided by feet. So these two units are going to cancel out. Anything divided by itself is 1. So I'm left with 1 times inches, which is just going to give me inches. All right, so this is how dimensional analysis works. The metric system is based on the number 10. So when we talk about converting within the metric system, I find it very convenient that our number system is based on the value of 10. So if we think about this, we have the ones place, the tens place, the hundreds place. So this would be 1, this would be 10, this would be 100. And what did I do? Each time I just simply moved my 1 into the next spot, into the next place value. Or you could look at it, if I had written my decimal, maybe I move my decimal 1 place, and then that's going to give me the same concept of it's all just based on the value of 10. So when we look at the metric system, our metric system is also based on a value of 10. So if I am converting from decimeters to centimeters or centimeters to millimeters, I'm simply multiplying or dividing by some factor of 10. Now there's a few different ways to think about how these prefixes or metric units relate to each other. So here I have it kind of written out horizontally where you can see that the values on the top of the chart are larger values. You can also notice that those are whole numbers. The values on the bottom half of the chart are written as fractions, which tell us that it's going to be smaller than that middle row right there, which is called the base unit. So the base unit is what we will be dealing with whenever we don't have a prefix. So what would some base units be? Well, in chemistry, you probably dealt with grams. In this class, we will deal quite a bit with meters, which would tell me how far, a length, a distance. Grams would be my mass. Perhaps in chemistry you dealt with liters. If we're dealing with time, it would be seconds. So these would be base units. If I were to write this, I would just put a G for grams, or I would just put an M for meters. If we have something that is in the metric system but it's not a base unit, we're going to take this first letter, typically, deca's a little special, but we're going to take this first letter and we're going to throw it in front of our base unit, and that's going to tell us what unit we have. So for example, millimeters would be an MM. Milligrams would be an MG, where this G and this M represent grams and meters, and the leading M represents the prefix milli. kg would be kilograms. km would be kilometers or kilometers. All right, so that's the difference between the base unit and then these other columns that represent our prefixes. Here are just some common metric units that we will be using in this class, and we'll learn these as we move through the different chapters throughout the semester. All right, so here is just another visual for the metric system. You will be expected to know what these prefix relationships are. Kilo is the largest that I will expect you to have learned. Milli is the smallest. If you looked at the previous chart, the range was a little larger, but this is what you will be responsible for knowing for my class. I learned the acronym King Henry died by drinking chocolate milk my sophomore year of high school, and I continue to use it today. It's a very convenient way to help me remember my prefixes. King would be the K for kilo. Henry, obviously is hecto, died. Now, for deca, it should always be represented as 2 letters. Different texts will use different secondary letters here, but deca is going to be a 2-letter prefix. I pretty much never use deca in my class, so ask if you're unsure, but it's typically not going to be deca. The word bi stands for the base unit, and again, this is where my meters, grams, liters, seconds, if it's time, that's where they belong. Drinking is going to be the column for deci. Chocolate is for centi, and milk is for milli. So this is the acronym that I used. If it's helpful, please feel free to use that. At the bottom of the chart, you can see I have a few different ways to numerically represent how these prefixes compare. Notice again that the base unit is my point of reference. So if I'm going from base to milli, you can see I'm moving to a smaller unit of measurement because that's a fraction or a decimal, or my exponent there on my 10 is a -3. That should be an exponent. Sorry, when I transferred the file into this particular program on my iPad, the font doesn't always transfer correctly. You can see on the left-hand side, those are values that are larger than our base unit. So a kilogram or a kilometer is going to be a larger unit of measurement than just a meter. In this class, we use meter sticks. So 1 meter stick and 1 kilometer are definitely 2 different things, and you can see here that the values are really all just changing by a multiple of 10. We're changing by 10, 100, 1,000. I'm moving my decimal place 1 place, 2 places, 3 places. So the metric system works out really nicely in coordination with our regular number system. Here I have a couple of examples. I'm really just going to do the one for 60 millimeters being converted into meters, and I'm actually going to come back here to this screen, and I'm going to write on this screen. So first I'm going to show you, using dimensional analysis, how would I convert 60 millimeters into meters. So this is the same as 60 over 1, so that's my numerator. I'm going to multiply, putting millimeters in the opposite location from where it started. So it started in the numerator. I will put it in the denominator, so that will cancel out. And then I'm going from millimeters to meters. The larger one gets the 1. Now, how many millimeters does it take to make a meter? Each prefix is a factor of 10 for this range on the metric system chart. So I am 3 columns away, so it's times 10 times 10 times 10. So 1,000 would go in my denominator. I would multiply across. My millimeters cancel out. So 0.06 meters, or you could say 0.060 meters. Okay? All right. Now, I have a different way to go about working this problem. It requires you to know the metric system chart from kilo to milli, which you're responsible for knowing either way. You will be expected to perform calculations using dimensional analysis. This little trick that I'm going to show you only works for the metric system, so you cannot use this if you were converting time from seconds to hours, all right? But here's how this would work. I start with the number 60, and I'm going from the millimeters column, and I want to transfer it to the base unit column because that's where meters belongs. So in order for me to go from millimeters to meters on the chart, I would have to move 1, 2, 3 columns to the left on my chart. So I'm going to come to this number over here of 60 millimeters. If I had a decimal, because that was a whole number, it would be located to the right of the 0. So since I moved 3 columns to the left on the chart, I'm going to take my decimal and I'm going to move it 3 place values to the left. Any empty spots here, I would just fill in with a 0. So when I look at this, I have 0.06, and that would be in meters, or 0.060 meters, okay? So taking my decimal and moving it so that it is mirroring how I would move on the chart. That's going to give me what my new answer would be after I have converted. So again, this is a neat little trick, but it only works for the metric system.